presentation and what are the grading policies for the final presentation to make sure that everybody is on the same page. Okay. So as we have went through the process several weeks ago about like finding the suitable project, I think most of you have already sent me the title, and I think they are appropriate, so you can just go ahead. But if like some of you might still struggling to find the appropriate topic, please try to do so, because the presentation time will be on January 5th and January 12th, which is like the final exam week and the week before that week, okay? So you don't have too much time to proceed, but at least you still have 1 month. So please keep in your mind that you need to do oral presentation for 20 minutes, and also following the 20 minutes oral presentation in English, there will be a 10 minutes question and answer section, also in English. And we'll do the presentation on Google Meet. The reason is because you will have, you know, like you will prepare some slides, and I hope that you can try to do the presentation as if you are, you know, participate in some kind of conference, okay? And I think, you know, like doing in front of the screen, there's a, you know, short note or something, so it will reduce the difficulty for you to really present in English. But as a practice, I think that should be ideal. And also, there will be a final report that you need to turn in. Policy is that the final report need to be turned in by January 12th. Basically, the second time of the presentation, you need to prepare that. So, for example, if you prepare at January 5th, then you have another 1 week buffer, so for you to turn in your final report. But if you participate the presentation January 12th, you need to turn in the final report on that day, okay? So it will be a hard boundary, so please remember January 12th is the hard boundary for turn in the final report, okay? Two parts that I think we have went through some point in the semester, and the last, the main point for today's discussion is about the evaluation and the preparation final project, okay? So I think the choice of topic section is already passed, and so I think I'll just skip this part, okay? So now I'm going to talk more about the presentation and the report. So I want to emphasize one thing, that why do we want to do presentation in such an advanced, you know, course? The reason is because I think at this level of the difficulty, usually it is the time for you to develop some taste and some practice about how to do research, instead of just, you know, taking the course and learn all the calculation detail, okay? So I hope that this final presentation can give you a chance to explore the world and try to, you know, spend some time on the subject that you are interested in, okay? So, of course, we don't want you to, you know, just learn things, you know, by yourself. The point is that we want to learn how professional physics learn stuff. So basically, professional physics, they learn things together, which means that if somebody learned the stuff or the subject carefully, they will try to share their knowledge with their peers, like share with their colleagues or share with their students. So the point is that we want to learn how to learn stuff together, okay? So that's the reason why I think we designed this final presentation, because presentation is the simplest way for you to communicate with your colleagues or like your friends. So the report, on the other hand, is another way to help you organize your thoughts and try to prepare a logically sound documents to make sure you really through the subject and you understand how things went. Okay. So basically that's the designing principle. Okay. So another thing is that the guideline here try to help you to develop these skills. So the most important thing during the communication is that you need to make sure that you are on the same page. Okay. You don't want to have a discussion with your friend and you are saying something with enthusiastic mode, and on the other hand, your friend is understanding something else. So what you are trying to say did not really convey through this communication process. So the first important thing for a presentation is you need to make sure you and your audience is on the same page. So you need to define the problem. Okay. So what is the topic? What is the problem that you are trying to understand? Okay. And the second thing that when you are doing the presentation or when you are discussing with your friend is that you need to motivate them, which means that you don't want to share some subject that your friend is not interested in. Okay. So if your friend does not feel like it is a very interesting subject at the very beginning, what you are trying to do is try to find some interesting stuff and make the conversation interesting. Okay. So this part is about the motivation, like why it is interesting. Usually when you try to read the literature, the introduction part usually is trying to do this job. So when you're writing a paper, you also need to learn how to motivate your reader. Okay, so that's why I think this process is very important. So during the preparation of your final project, you should always ask yourself this kind of question: why it is interesting? Like, if it is interesting, whether it is interesting only within certain sub-area, or it is actually quite interesting across different disciplinary. Okay, so if you are able to find some reasoning that the subject that you are studying actually is very, widely applicable on different subjects, then usually people will feel more motivated and they will have more desire to understand what you're talking about. Okay, or there are some other ways to motivate. This is something very new that it never appeared in other areas of research because of certain reasons. That will also be another way to motivate your audience or reader and try to make the conversation more fruitful. Okay. So the third thing is that, of course, we are physicists. Okay, so we need to understand what we are talking about in a precise manner. Like what I mean by that is not to write everything in terms of equation. Instead, you should try to convey a clear physical picture. Okay, usually, like during the presentation, mathematical formula or numerical data cannot directly convey the physical concept. The key concept usually is conveyed through a physical picture, and those are usually part that's most challenging to have, because you really need to think hard and try to describe things in terms of a pictorial way. Okay, so the point is that we want you to try to focus on the subject that you're trying to explore and try to find the key mechanisms and try to explain those key mechanisms in terms of physical concept instead of doing, just mathematical derivation and numerical data demonstration. Okay, and the last part is when you are preparing your presentation, you should always ask yourself this question: what could we learn from the topic? Okay, not only yourself but also for your audience. Like, your audience might sit there and listen to your presentation for 20 minutes. What kind of information that you're trying to share with your audience? Okay, so these are the guideline for you to prepare the report. So, okay, so let's try to start from the definition of the subject. So usually the definition of the subject should contain a short introduction about the topic, including what is the background of the topic and what is the definition of problem. Okay, and here there are some motivation that you should always try to ask yourself, like, in addition to the big question that I asked, like what do you choose this subject, why it is interesting, there are some final questions that you can ask. For example, you ask yourself, what is the conceptual non-trivial part for this project? Okay, try to identify one or two of the conceptual non-trivial part and try to convey them through a physical picture. Okay, and this conceptual non-trivial part came from theoretical or experimental observation. They are both very nice, but you need to demonstrate those and try to convey them during the presentation. Okay, and also the last part I already mentioned, you should ask whether this conceptual interesting or useful thing is within this field, or maybe it can be applied to other fields. Oops. Okay. So how the mechanism work? I hope that you can, during the presentation, you are able to show what is the assumption and what is the physical argument and how it is derived. Okay, so here how it is derived does not go through the equations. Instead, I hope you can focus on the logic and with some suitable details. So don't be bugged by the paper that you're reading that maybe there's some key equation that you don't know how to derive it. At least you need to have some argument or like try to some extent guess why it is a reasonable result. Okay, and of course, like the reason that we want to focus on how this mechanism works is that we identify the primary mechanism. So please first try to identify what is the important mechanism, then try to understand it, instead of try to understand every mechanism at the very beginning. Okay, because some of them might not be that important. Okay, so you should have after you read some of the literature or the documentation, you should have some idea about what is the most important mechanism and what is the secondary one, etc. So that you will have a hierarchy of concept that you should try to start with. Okay, and also after you explain what is the mechanism, please also explain what is the implication that it provides. Okay, so about the last part, what could we learn from this subject? In more detail, one of the ways that you can try to, or some of the questions you can try to ask yourself to this type of question is like, for example, how it is connected with experiments, because sometimes you might have some theory or some phenomena that is motivated by some obscure experimental data. Okay, and maybe you can also ask how this interesting subject connect with other theoretical ideas. That could also help you to identify why this work is important on a global view. Like maybe because of this discovery, it inspires later studies on certain type of subject. Okay, so this kind of logic is very important. And the last one is actually something that you should always ask yourself if you are doing research. How does the idea change its previous understanding of the field? Okay, so why I'm trying to elaborate these things is because when you are trying to do a research work, when you have some idea about how science is structured during the history, then it will help you to identify the important question. Okay, once you know what is the important question, then you will have a better chance to make important contribution. Okay, so that's the logic, and this course is basically, or this final project is basically try to train you or try to give you some opportunity to see whether you can understand the subject and to see whether you can identify the key idea that how it changes the historic development of the science advance along this line. Okay, so always keep in mind and try to ask yourself this question: how this idea changes previous understanding in the field. Okay, so the next part is something that I didn't really discuss very carefully during the semester, but I want you to know that there will be an evaluation about your final project, and the final project will take 40% of your final scores, and 20% of them will be related to the presentation. And this evaluation will be based on mutual evaluation, which means that when you are doing the presentation, your classmates are actually grading your. So that means that even though you are not presenting that day, you still need to participate the lectures, okay? So there's no excuse like, like during the semester, maybe you're not there. I'm fine with that, okay? But during the presentation, you need to provide some grades for your classmates, okay? So on those days, I'll basically check the participant whether you are showing or not. That's the only 2 days that I'll check whether you really show up. So please make sure that you are able to take the final project, okay? So the detailed evaluation sheet, I will provide it later, but basically I'll say something more about that. And after this presentation, which is like taking like 20% of your total score, your report will be graded by me, and I will also, and that part will take about 20% of your final score, okay? So on the evaluation sheet, basically, I hope that it just give you a, more like a coarser grades. Like if you feel like the presenter is doing an excellent job, you just give A. And if you think it is okay, then you give B. And if it is really needs some improvement or something, you can just give C, okay? So, so what are the evaluation points for your presentation? The first thing is, of course, the logical structure. I hope you are not just giving a presentation and saying that, oh, I have this line and I derived this line, and the next line is by doing some kind of summation over some. I don't want to do that, okay? So try to give a big logic about why you are doing this and what is the implication after this equation or like after this result, okay? So the logical structure is very important. And also, sometimes you just give random statement, like maybe you are giving a presentation about subject A, and you mention subject A, there's a random point, conclusion 1 and conclusion 2, and conclusion 1 and conclusion 2 did not really connect, and then you get a conclusion 3, and you say conclusion 3 is really important, okay? That kind of situation, I want you to avoid that. So before you do the presentation, please try to find the logical structure of your presentation and make sure it is logically coherent, okay? And the second part is about the content of the talk. Of course, that includes like, whether you have a theoretical, like good theoretical background introduction and also like something related to that. And also presentation clarity, that also includes whether you show some, cartoons or like have some tables to show the numbers and things like that. And the last part, and the next part is like a Q&A, because you will have questions after the section, and we will also evaluate. I will also ask you to evaluate the presenter's performance during the Q&A section. And the last part is also very important. Do you feel you learned something? Okay, so after you listen to the presenter's presentation, maybe you found that, oh, this is a very interesting subject because the presenter is doing a very well job that I can basically learn from him or her, okay? So the last part is like, please take care of that, because sometimes people don't care about whether the audience understand or not. They just say whatever they like to say, and that usually is a sign for bad presentation. Okay, so about the logic structure, I think I already mentioned something that you need to mention, like you need to focus on what are the assumptions and what are the implications. And also one of the simple question that you can ask or you can tell whether the logical structure is coherent is whether the speaker can tell a story or give you a full picture about the subject, okay? So it includes several things: background, motivation, and what are the works that I have done previously, what are the key concepts that changes everything, and what are the conclusions they got. And the next thing is that during the 20 minutes, for a 20 minutes presentation, usually I will suggest you to have a short outline, okay? If the talk is 10 minutes, I will suggest you don't need the outline page because it's just too short, okay? But 20 minutes talk, usually it is long enough for you to have a simple outline. And then And sometimes people will have some false advertisement, like in the outline you say something very big, but eventually during the talk you did not, say everything. So that will also be not really good when you are doing a presentation in a conference. So please try to design an outline and make sure that you are able to cover them in within 20 minutes. Okay, so about the content of the talk, hopefully every subject there should be at least three parts of the subject. One is about the experimental part and the pure theoretical part, and also some numerical evidence. Okay, so but depends on the subject. Hopefully you can at least find two of them. For example, if it is just purely theory, usually it is not going to be very influential because experimentalists basically don't care. So if you have two out of these three research area that they feel like this subject is interesting, usually it will be a very good for you to show that this problem is actually very important because people are doing different kind of approach to the same problem. Okay. So about the content, of course, we care about the clarity, whether you can, whether the audience can understand what is happening, and whether the speaker can summarize the conclusion and describe the setting and connects the idea in a fluent way. Okay. So another thing is about the presentation clarity. Basically, these are quite standard. Like on the screen, you hope that you are not trying to use some font of like 9 point. Like basically, nobody can see what you are talking about. Okay. So try to make sure the font size is readable on the screen. Without any, without any effort. Okay, so if you are able to read the font size easily on your screen, usually it means that when you project that out, it is also comfortable for your audience. And also, please try to identify the key information, not cluttering all the information within one slide. Okay, usually one slide is for 1 point, like one of the main points you want to take. And also, the designing principle is that if you are going to talk about, if you are going to give a talk about 20 minutes, usually for the normal human being, one slide will take about 1 minute. So that's like a very simple count. And usually that's the upper limit, okay? So if you are giving a 20 minutes talk, at most you can give 20 slides, okay? But if it's fewer, that's good, because for example, if you have 15 slides, that means that you can have more time to make yourself clear for each slide, okay? And also another important thing for the presentation is please try to use visual aids, not trying to, copy paste the content of the paper, like the whole paragraph. This paragraph says something and you mark the important information. Don't do that. So during the presentation, the visual aids includes you use figures, you use some tables or like schematic plot to demonstrate the key idea for the physical picture, okay? During the Q&A section, it is also very important because the first thing is that the audience will ask you a question, and the speakers should try to make sure they understand the question from the audience and answer the right question, okay? So sometimes the audience might not understand what you are saying, so the question they are asking is not really right on the target. The little tip is that you are able to actually, as a speaker, audience or the one who has the question to explain themselves, like what they are really asking about, okay? That usually will be helpful so that your answer will be right on the target, okay? So during the Q&A section, we'll evaluation criteria will be whether the speaker can understand the question properly, and also whether the speaker, after the speaker understands the question properly, can he or she answer the question properly, okay? Because sometimes audience might ask some thorny question that maybe the speaker cannot answer quite well, but maybe it will be a very challenging question, or maybe it is simple, but the speaker cannot evaluate that. So can answer properly. So that will be part of the evaluation, okay? So the last part is more like, depends on everybody's feeling. Do you feel you learned something? Because I think, as I mentioned, a very for the presenter, it is a process for you to practice your presentation skill. But for the audience, we are actually trying to learn things from you, okay? So I think whether the audience can really learn things from you is also part of the grading policy. Okay, so about the report evaluation, basically it will be very similar, but you will have some room to describe what you have learned, or like maybe describe the subtle ideas in more precise manner, like equation or something, and build some further connection with different fields. But as I also mentioned, please don't try to, put down all the derivation detail. Just write down the key equation or key idea and how this key idea can be derived in principle, but you don't need to show me the calculation sheet about every equation. Okay, so I think that will be all about the final presentation. So currently, are there any questions about the final presentation? Okay, so if not, we will continue. Wait a second. How to get rid of this thing? Here it is. Okay, so if not, we will get back to the lecture. And also, I want to remind you that there will be there's a homework due today. If you did not finish it, please turn it in the envelope in front of my office by tomorrow at 5, I think, as usual. So let's see. I need to use that. And wait a second. To share screen. Okay. Wait a second. I think I didn't connect my pen or something. Okay, so now it should work. Great. Okay, so I think we will continue our discussion about the critical phenomena from the reviewing of our last lecture. Okay. So in our last lecture, basically, we discussed the local flow or local RG flow near fixed points. Okay, and the local RG flow is important because it basically controls the critical phenomena and the universality class concept. Okay, basically we can try to remind ourselves how does it happen. So basically we are trying to derive how the RG transformation on the scale of L that changes the coupling constant K. For example, if you are focused on K sigma, then you will take derivative about the K sigma, and you ask how this change is behaved by a particular fixed point K star. Okay, so the key information is that this thing usually we define it to be Y sigma. Okay, and in our simple problem of IC model, this sigma usually represents the most important coupling constant K, which is related to how these spins interact with each other. And also, another important relevant coupling is basically the external field. So you can also ask how the external field changes when you try to change the scale, or when you perform the renormalization group transformation. Okay. And another important thing is that when you are evaluating this object, you are always evaluating with respect to a particular fixed point. Okay. So whether certain coupling is relevant coupling or irrelevant coupling depends on what fixed point you are talking about. Okay. So during the last discussion, basically, we also mentioned another important fact. This RL, which is the renormalization group process, will actually provide an equation that connects the coupling at different length scale, but the expression is usually quite general. And also, they are usually highly nonlinear. Okay. But the key point is that we can still try to approximate RL. And the reason is because during the renormalization group process, we sum up a little patch of your system, which contains only finite degrees of freedom. So this RL should be an analytic function. So whenever something is analytic, we know it is a blast because we can tightly expand it, which is the favorite friend for physicists. Okay, so that's like the very vague or like a very simple-minded concept that what we are talking about. And the other important information that we have discussed is about the global renormalization group flow. And basically, it provides you the structure of your phase diagram, okay? Because the alternate destination of the RG flow basically was flow to a stable fixed point. And these fixed points usually have correlation length that is 0, and they are also characterize the particular stable phase. So from the global flow structure or the topological structure of your RG flow, actually you know the topological structure of the phase diagram, okay? Okay. And nowadays, the term topological is like a very popular, so I just want to make sure what kind of topology that we are talking about. So to define topology, you need to define what is the adiabatic deformation of like what you are talking about. So in general, in some coupling space, maybe you have some K0 and K1, okay? So maybe you have a phase characterized by a fixed point, let's call it F1, and maybe there's another stable phase, let's call it fixed point F2, okay? So what do I mean by topology here is that in principle, for different models, you might have different, like the coupling, the meaning of these K0 and K1 might be different, but you still have the fixed point F1 and F2, and because they are different phases, so there will be a phase boundary that separates these two phases, okay? So if you have another model which have similar phase, like similar RG flow structure, what does that mean? It means that you still have this fixed point 1 and fixed point 2, but the phase boundary of the phase diagram might be different, okay? But what do I mean by topology here is that the phase boundary is something that you can adiabatically deform, but the primary of your fixed point is not changing, okay? So that's what do I mean by the topology, or like the topological structure of the phase diagram can be inferred from the RG flow, okay? So the detail of the phase boundary, you may not that, but or like maybe it is not generic, but the structure might be the same for the same universality classes, okay? And also, I think at this point, I already used some sync of the stable fixed point. The sink of the stable fixed point means G flow basically will flow to this fixed point, and this particular fixed point is actually related to the bulk phase. Okay. So in our last lecture, we try to formally study the simple cases. Okay. The case 1 is a fixed point with one relevant direction. Okay. And we also consider another simple case is a fixed point with two relevant directions. But they don't couple with each other. Okay. And from the previous, or like the last lecture, we found some relation and at least in these simple cases, which is related to the two relevant directions are the YH and YT, okay? And we basically make a connection that, let me see what's the result. I think during the last week, we have derived that YT is basically 1 over mu, okay? So knowing the behavior of YT are the critical exponent that you should observe in the experiment, okay? So, so at this point, we are making very general assumption about the form of, at least in our last week, derivation, the form of RL is general. And today we are going to use a model to really see how this thing changes. Okay, so let's see. Okay, so I think that's something that we have left ourselves. And I think another thing during our last week's lecture is that we asked the question, what is the effect of irrelevant variables? Okay, so during the last week derivation, we basically focused on the relevant directions, maybe one relevant direction or two relevant directions, and we found that using the analysis along the relevant direction, we can get pretty close, basically according to the RG transformation RL that we derived. So the question that we are trying to ask is like, if there's, not if, like in general, for most of the model, they will have a lot of irrelevant variables. So what are they doing during the RG transformation? Okay, so to make the discussion more precise, let's try to remind ourselves what are the singular part of the free energy should look like. So let's use T and H to represent the relevant directions. One is the temperature and the other is the external field. And we might have some other coupling, K3, K4, and etc. And those are the irrelevant variables. Okay. As we know that when we are doing the RG transformation, you will have a scaling factor L to the pops up in your free energy expression. And following the procedure that we did last week, basically the after one RG step, the T lambda LT scaling form, and the coupling H will also pick up this scaling form. So have all the rest scaling form for these irrelevant operators similarly. So I'll just write them down as lambda 3 on the scale L. Etc. Okay. So well, let's see. Maybe I should try to shuffle things a little bit. Oops. Okay. So this is how the irrelevant couplings changes. What do we mean by relevant or irrelevant is basically these eigenvalues of the matrix M, lambda TL, and lambda HL will be greater than 1. That's called they are relevant operators. Equivalently, you can say YH and YT are greater than 0. Okay, so for the irrelevant couplings, for those lambda 3, lambda 4L, they are by definition smaller than 1. Okay, they are called irrelevant is because after you do the RG transformation, because these eigenvalues are smaller than 1, basically they will get closer to 0. So here we are assuming that these couplings like TH, K3 tilde and K4 tilde are all decoupled. That is, we are already working in the basis of M. Okay, so this assumption is not really, harmful because eventually we are going to diagonalize our matrix M and analyze how the scaling couplings transform after you perform the RG transformation. Okay, so now from here we know that this is basically, one step of performing RG. So as we have discussed previously, in principle, we want to perform this RG transformation iteratively. So after several times, for example, after n step of RG process, we have this expression. L to the n to the minus d because we perform it n times. And now we will have t times to the yt times. And this is because by definition, this lambda L, the solution for this lambda L basically will be L to the power of yt, and when we perform this transformation n times, we basically will get this vector. And similarly for h. Okay, and also this expression for 3, so I'll just write it down. And now we use y3 to represent the scaling factor, but remember they are irrelevant, so y3 is smaller than 0. Okay, so you got tons of them. And the trick is still the same. We try to identify this object with something which is called B. B should be something that is of order 1. So once we do this identification, what we are doing is actually we are able to make the replacement that Ln should be replaced by B divided by T to the power of yt. Okay, so I think we will continue this simple calculation and discuss a little bit about what could happen for the irrelevant variables. Then in the next lecture, we are going to discuss model, which is ISIN model, such that we can really do some calculation and see how the error are constructed. Okay, so see you after 10 minutes. Okay, so we will continue our calculation. So as usual, we will take the relevant direction, for example, like t, and try to use that to find a suitable larger number of order 1, basically b, such that when length or the calculation are more or less controlled because the fluctuation is small. And by choosing that value of b, basically what we are choosing is that we are choosing the behavior of the wait a second. Why it is not connecting? Okay, that's good. So basically, we're choosing the scaling L to the power n's behavior and try to re-express it using the relevant direction t and this order 1 big number b. Okay, so if you replacement and put that plug that in, then what we are getting is actually an expression that basically looks like this. Wait a second, I think not. So basically, we will get t divided by b because there's a minus sign here, and d divided by yt. And the function f is going to be replaced by f of b, and the h times t divided by b to the power of minus yh divided by yt. 3 tilde, but now with t divided by b to the power of minus y3 divided by yt. Okay, 4 tilde also looks like this, and etc. Okay, so basically all the rest are those irrelevant couplings. Okay, so as we know that the y3 and y4 basically they are smaller than 0. So we take a look at this expression. The exponent of these irrelevant couplings will basically be greater than 0. And for those exponent, when you send t goes to 0, basically for example, like take an example of y3, this coupling will goes to 0. Okay, so this is to some extent that we anticipate because the irrelevant couplings will go to 0 as we are approaching the critical point. So the question is, what we are trying to do is that we are sending t go to 0, we should have something, basically our the singular part of our free energy, and we are trying to ask, is it going to be something that looks like this? Okay, why there's a question mark? Because here we make a replacement that because when t goes to 0, this argument is sent to 0, but we kind of make the bold assumption that when we send in this variable to 0, we can really replace its value by putting the okay. So why this question? There's a question mark is essentially because here we assume we made toggle to 0, basically it's analytic. But there's no a priori guarantee that it's true, and frequently it is wrong. So when you are able to make this simple replacement, then nothing strange is going to happen. But there are is that f is actually singular, so you are not able to make this type of replacement. So if this happens, that is f is singular as the irrelevant variables vanish. The irrelevant variables plays a function. So we give it another name. Dangerously irrelevant. Okay. We probably will not see an example at this moment, but I just want to remind you at this point, there are something that is a bit subtle considering the irrelevant operators. Okay, so now we are going to do a more exotic example, which is the RG for 2D isometric. Okay, so in the homework of the 1D isometric model, it is the example where you are able to perform the calculation exactly and try to map out the RG transformation, and then you will see how the couplings changes as you perform the RG. Okay. However, you should also get the conclusion that the RG is a little bit boring because you just flow in one direction. There's no such thing like a critical point or like critical fixed point in the one-dimensional system. Okay. So here today we are going to present a calculation about the 2D isometric model, where you can explicitly see that the RG transformation suggests there's a special fixed point, which is what we call the critical fixed point, and then the RG flow will be a little bit non-trivial, and maybe you'll feel like it is more exciting to adopt this method to various different systems. So, but also, in RG flow came with a price. The price is basically you are not able to do the transformation exactly as you have done it in 1D. It involves some kind of approximation. So basically, includes the approximation for RL. Okay, so as I mentioned, I think you will see why deriving this RL is difficult in a two-dimensional model. You will also see what kind of assumption or approximation we are making to approximate this RL, and how this approximation of RL can lead us to the critical exponent in this model explicitly. So it is a little bit complicated, but I think at this moment we don't need to worry too much about that. So let's try to set up the problem. So let's assume that we are discussing a IC model. Let me be more specific. We are discussing about a ferromagnetic IC model on a triangular lattice. Okay, so you will probably see later why we want to discuss the physics on triangular lattice. But what I'm trying to convince you is that for ferromagnetic system, it doesn't matter what kind of lattice you are sitting in. For example, if you are sitting in a square lattice, ferromagnetic coupling just says that all the spins should try to align themselves with each other. So that's what happened on a square lattice. However, on a triangular lattice, I don't know, let me try to draw some of them. Okay, you still have some spins sitting on the vertex. If they are ferromagnetically coupled, they also want to do only one thing, try to align themselves. Okay, so on a triangular lattice, something novel will happen if it is. Let me try to write down. These are ferromagnetic. If it is ferromagnetic, something non-trivial could happen. For example, if the system is anti-ferromagnetically coupled, when you put two spins, they will try to arrange themselves in this fashion. Then the third spin does not know what to do, because either you can point in along one of them, but it will be, the other spin will be unhappy. So this is what we call the frustration. Okay. We are trying to discuss a simple case instead of discussing this in like a more exotic or interesting scenario where frustration happens. Let's try to focus on the ferromagnetic one. Okay. And the reason we are going to is because we want to define a particular cross-graining scheme that you will see what will happen. Okay, so ferromagnetic IC model on triangular lattice. Let's try to write down the Hamiltonian. Here, for our purpose of analyzing, we already include 1 over kBt into our definition of Hamiltonian, so that we don't need to worry about the dimensionality of our coupling. Focus on the coupling, which is dimensionless. So the Hamiltonian will look like this. It will look like K times the nearest neighbor coupling, and field H. And all these K and H are basically dimensionless. Okay. So remember that ferromagnetic means that here the definition of K is beta times the coupling J, and ferromagnetic means this J is smaller than 0, so all the spins are, they prefer to be aligned with each other. Okay, so let's start our RG process. In order to do RG, you need to define some kind of cross-graining process. Okay. So here we are going to apply one of the cross-graining process called the majority rule. Okay. So let me try to be more specific about what it is. So let's see how to do that. Okay, let me try to draw everything at the first step. Okay. In a portion of the triangular lattice, and we should understand that the spins are sitting at the vertex of this lattice, okay? And even though it is not so nicely, but you can still tell it is a triangular lattice, okay? So now we are trying to collect the spins in certain fashion for us to do the cross-graining process. That's too thick. So let's try to do this. So now I'm drawing this plaquette using the pink color. So you can see that every spin on the original triangular lattice must belong to one of the pink triangle, right? For example, these three spins belongs to this particular pink triangle, and these three spins belongs to this particular pink triangle. These three spins belongs to this one, okay? So no spin is left, okay? Every spin can be, recategorized according to which pink triangle it is sitting. And within this pink triangle, what is the position it is at, okay? So let's try to define another thing. Let's say for this particular pink triangle, we can give it some kind of label that this is the side 1 of the pink triangle, and this is the side 2 of the pink triangle, and this is the side 3, okay? So for the blue, in order to specify which spin it is, you can give me two information. One is which pink triangle, and the other information is which subindex, that is 1 or 2 or 3, okay? So we can use capital I and J to represent the information about which pink triangle, and we use 1, 2, 3. What are the subindex for where this particular spin is sitting at, okay? So then after we divided to these different patches of spins, what do we mean by the majority rule is that, for example, for every spin configuration in here, I'm just drawing a random one, okay? This one should be okay. So I'm just randomly draw a spin configurations on this blue. Let me try to zoom it in. So, okay. So the majority rule is that maybe I should try to move it a little bit too. There's a cross-grain degrees of freedom, which we call SI, and this subindex capital I represent, one of the pink triangle. On this pink triangle is defined as the sign of the summation of the spins that is belonging to the same. Okay. So the first thing is that the sign of something, it must be +1 or -1. So for cross-grain, because it automatically provides us the new variable that is basically identical with the previous Ising variable. Okay. And the second thing is that because we are talking about triangular lattice, so spins, which is like 1 or -1, 3 of them added up, it is either +1 or -1. There's no chance to be 0. Okay, so this cross-grain process will be well defined. So let's try to take a look about the majority rule. What are the spin configurations for this particular spin configuration of the original spin? So for this block, the cross-grain SI should be 3 plus add up together, it will be plus. So this one is +1. And for this particular plaquette, the cross-grain, let's call it I prime, will be 2 up. It will still add up to be +1, so it is +1. And for this particular triangle, we should have 2 -1 and 1 +1. So when you add it up, the SI double. Okay. So this is the cross-graining process for us to map it to the new variable. Okay. Yes. The question is, if I pick a little spin, this blue spin, will they belong to 2 different pink triangles? The answer is no, because you need to choose your pink triangle wisely. For example, let me draw a green one, which is the wrong choice of the pink triangle. So if I choose my pink triangle right here, right? Then what is going to happen is that this blue spin will belong to the pink triangle and the green triangle at the same time. But that's not what we want. We want it to have a unique label, which means that when you are trying to, for example, when you construct your first pink triangle here, right? Then basically these 3 spins are used up. So when you assign your next pink triangle, you cannot touch this spin. As I mentioned previously, you want to preserve the symmetry of your system. So to some extent, you still want your system to go like structure. So if you cannot put it here, then the choice we are using is we try to put it here. So if you choose this second pink triangle, then every spin is covered by 1 pink triangle. Then the third pink triangle, you cannot choose this one because it will touch the upper one and the lower one. So you decide to choose another one that's a little bit further away. So in this pink triangle, you actually need to design it in a particular pattern. And here I'm writing a relatively small portion of the system, but you can probably already see this pink triangle itself form some kind of let me try to use another color to try to draw why it is a triangular lattice. Okay, so this is a set of lattice, but this new set of lattice is still a triangular lattice, but it's kind of rotated by 30 degrees. Okay, and the new degrees of freedom is cross-grained SI at the vertex of this new green triangle lattice. So at this point, you can already see that the lattice scale changes by square root of 3. You need to stare at this geometry, and then you will convince yourself it is square root of A, square root of 3 times A, and here A is the original lattice constant. Okay. Can you say it again? It's too unique. Yes. So first, the SI can be only plus or minus 1 for the little triangle. And here we only consider the sign of it. Oh, the question is, oh, now I understand your question. The question is, if we look at the microscopic, these little blue spins, one of them will have 3 spin up, and the other have 2 spin up and 1 down. Why can we assign them to be the same configuration, right? At this moment, I'm not saying they are exactly the same. At this moment, I'm just trying to say this is a cross-grain process. Cross-grain process means that you can do this kind of assignment. But the question is, after you perform this assignment, still use this new assignment to construct your partition function. Like, you know, there's a partition function that you need to solve. And then you try to develop some scheme to sum it. This defining scheme is just the intermediate product. This intermediate product may not have like direct physical meaning interpretation of your system. Okay, so another way to say is that when you're doing cross-graining, to some extent you are trying to erase some information that is not relevant. At this point, this cross-grain process seems like you drop a lot of information. For example, you can no longer tell whether you have 3 spin up or 2 spin up and 1 down. And more or less, you are trying to say they are to some extent, but not at a more microscopic scale, they are different. But if you try to understand the behavior on a more rough scheme, then you will are related with each other. So at a microscopic scale, you're right. Once you do the cross-graining, these 2 degrees of freedom are not the same. Okay, but when you are doing RG, what you're trying to do is do the microscopic effect and try to consider a physics that is on a broader length scale. And we are trying to do that at this step. At one step, it looks very not so, you know, that you perform this process many, many times, right? So at this point, you have 3 spin up. And in the next step, you are going to do the RG process again. And maybe you will have, I don't know, you need to sum up to have 9 spins. And in these 9 spins, maybe some of them are spin up and some of them are spin down. But when you iterate this process, you are summing more and more spins. Then the difference between 2 up, 1 down, and the 3 up is smaller and smaller because you are consider a patch that is larger and larger. So that's another way to think about why this kind of process is not going to, you know, erase too much information. The physics we discussed is on a scale that's supposed to be have a longer length scale. So when you have a longer length scale, that means that the microscopic degrees of freedom within this longer scale, there are more of them. So when you are summing them up, there might be some little difference. But when the patch is larger and larger, this little difference becomes less and less important. Yeah. Can you say that again? Okay, so there are several steps to tell whether RG step is legal or not. One is that whether you sum them up, they are going to, like if you sum up all the SIs, will you get back to the original partition function? Remember that there's a differentiation operator. There are 3 of them. One is to keep the invariant, and that condition is that the summation of the projection operator needs to be 1. And the other is this projection operator needs to be positive definite, and you will reflect the symmetry of the system. This process, you can try to check this cross-grain process, basically will satisfy these 3 criteria. And if that checks, then probably you will see why cross-graining is actually not a too bad idea. Yeah. But that's a good question. You should try to challenge yourself why I can do this kind of cross-graining and what is the reason behind. Steps further, probably you will have a bigger picture and you know why this is going to be a valid question. So usually this question should be asked in the following way, okay? So if you look at the equation, mathematical equation, you'll ask why I can do that, okay? But if you are trying to ask it in another way, if I'm caring about some other physical property, can I do this operation but still get the physical property I want, okay? So if you are able to convince yourself the physical property of the question you are trying to ask is not going to be, then this step is okay. Yeah. So let's try to move on and see out of this cross-grain process, okay? But before that, other than this cross-grain validity, are there any other questions about the structure, the cross-graining process? Okay, so if not, move on. So let's see. Okay, so I think I already did some of the drawing, but let me try to draw it again. So basically, after this cross-grain process, we will have 3 degrees of freedom. One is SI, the other is SI double prime, and they basically live on a new triangular lattice with lattice constant square root of 3a. Okay. At this point, we have the information that L is basically square root of 3. Okay, because it is like the scaling variable that we have previously defined. Try to construct an approximation RG scheme with this cross-grain process. So before we do that, let's try to have some side remark about exact results. Okay, so here I'm not going to show you the exact solution for 2D Ising model. All you need to know is that basically the exact result is obtained by Onsager. And the critical exponent that's given from the Onsager solution is alpha is 0 and delta is 15. Okay? And combined with the previous understanding that critical exponents depends on each other. So you can use these 2 free variables to construct all the critical exponents if you want, okay? And the fact is that you are going to get basically, let's see, you are going to get mu equal to 1 For previous derivation, we know that mu is basically equal to 1 over yt. So we immediately get the conclusion that yt is equal to 1. Okay. And also, you can try to derive t by using this information. And there will be an exercise for you to play with that you can show that delta equal to d plus 2 minus eta divided by d minus 2. Okay, and because of this thing, it's basically 15, and in 2D, we know d is equal to 2, so you can solve basically eta is 1/4. Okay, so when you can plug that into the scaling relation or the scaling rule that we previously derived, and plug the information that the of YH is equal to 15 divided by 8. Okay. So these two information is the important information that we would like to check. So at the left panel, what we are here is not really, deriving the YT and YH directly. Instead, we are assuming that we know Onsager's solution, and providing the Onsager solution gives us two critical exponents for the YT and YH. And here I'm just very quickly show you that what is the value of YT and what is the value of YH. Okay, and the reason we want to use that is because we want to make a comparison. It doesn't require you to solve it exactly. So if we are using RG instead of solving the model directly, can we get something that's close to this value of YT and YH? So that's the goal that we are trying to achieve, okay? So because we already know this scaling factor L is square root of 3, so we immediately get the conclusion that the eigenvalue of T should be power of YT, and because YT is 1 here and L is square root of 3, so we know lambda t should be something like, I don't know, square root 3, which is something like 1.732. Okay. Similarly, we can try to evaluate what are the eigenvalue lambda h, and it is L to the YH, which means it is square root of 3 times 15 divided by 8 to this power 15 divided. And if you use the calculator, it basically will be 2.8. Okay, so the point is that this lambda t and lambda h will depend on your scale L, because it is L. But the key point is that this YT and YH should be independent of the L. Okay, so we will see how to calculate this YT and YH using the approximation scheme. Okay, so set our stage, and let's try to move on. So we basically define what is the cross-graining process in our previous step, even though at this moment it looks quite kind of suspicious, like why I can consider this thing or like cross in this way. Okay, so so let's try to move on and try to take this approximation as a valid approximation. So so the first challenge we are trying to make is that we want to find a label to represent the original spin operators. Okay, so let's try to describe what we are trying to do. Next, we want to formally represent the Hamiltonian. Okay, so let's remind ourselves the structure that we have in mind. Okay, So here I use some dash bond and solid line to remind ourselves how we divide our patches. Okay. So also I want to remind ourselves what are the sublattice index 1, 2, and 3. So let's use a two-pole sigma I, which is then by the spin configurations for this cross-grain spin, but labeling the three different sublattices. Okay. So we also try to remind ourselves the majority rule of SI, or the cross-grain spin, is actually the sine of I1 plus SI2 plus SI3. Okay, this is the majority rule. Not super satisfactory, but let's try to move on briefly. So let's take a look about what are the possible configurations of this SI 1, 2, 3. Okay, so basically we have 3 spins. Every spin we have 2. So all the configurations are 2 to the power of 3 of them. So there are 8 of them. Okay, so let's try to focus on the case where there's no magnetic field. So we can focus on the simplest non-trivial analyze. So question is, what are the possible value for, or like what are the possible combination for this two-pole sigma I? Okay, so let me try to write them out. So for the sigma I, we could have the two-pole that all spins are pointing up, and 2 up, 1 down, and the cyclic permutation of them. Okay, here are 4 of them, and the 4 of them that I listed are all having the property that after you use the majority rule, they will give you one spin configuration as I equal to plus 1. Okay, because those are the configuration where upspin is more than downspins. And similarly, you can try to consider other 4 configuration by basically flipping everything. And these 4 will correspond to the case after you do the majority rule, you got a block spin minus 1. Okay. So at this point, everything is quite specific. So to get back to the microscopic configuration, there are several ways to do that. One is you give me a set of SI value, okay, and this SI value is basically depends on the majority rule, okay, and once you get me the configuration for this cross-grain spin, you miss some information, because if I have this cross-grain spin to be plus 1, I actually don't know which microscopic spin it is. Okay, so in order to specify one-to-one correspondence with the original microscopic spin, you need to specify the other set of sigma i's. Okay, so that if you give me what are the possible SI and the corresponding sigma I for each triangular block, then I can recover one-to-one of my original microscopic spin configuration. Okay, so combining these 2 expressions, we should be able to recover the microscopic. Okay, so at this step, are there any questions? Oh, by the way, I forgot to mention that the icing spin, there are icing spins. So from this cross-grain process, you can also see the Z2 symmetries there. Okay, so that's something that I should emphasize because a well-defined cross-graining should respect the symmetry. Okay, so now let's see what we are trying to do. So in principle, what we are trying to find is the effective Hamiltonian, let's call it H prime, which is Hamiltonian with the variables of the Bloch spins, which is a variable of this set of these SIs. Okay? And how to get that? The idea is that we originally what we are doing is that we are trying to find this, this partition function, right? But now, instead of doing that, what we are trying to do is that we try to sum over just partially the little spin configurations sigma I. And this little spin configuration is that for each triangular plaquette I, there will be at least a such little spin configurations. And we try to sum them up. And in principle, our Hamiltonian can be expressed exactly using these new sets of variables, right? As I already tried to convince you that for each microscopic configuration, I can always use this Bloch spin SI and the configuration within each Bloch spin, the sigma I, to label this microscopic configuration. And in this summation, if I try to sum over this little spin sigma I, in principle, I think I'm writing it in a bad notation. So sorry, let me try to pause a little bit and try to collect things. Otherwise, it will sound really confusing. Okay. So let me try to restate what I'm trying to say again. So this is the original Hamiltonian, nothing's changed. We just define the partition function and we just sum over all the little spin. Okay? And how to understand this partition function if we want to sum them according to the Bloch spin SI and the configuration within each Bloch spin SI, that you sum over two sets of variables, and each, like combining each configuration of SI and sigma I, basically you get one of the spin configuration as little I. Okay. So what you are doing right now, like this equality is really the equality, it holds for, forever, because we are just summing things in a different manner. But what we are trying to achieve is actually we want to get this part and express it as this thing. I should keep my notation consistent. There should be no minus sign because I use minus beta in the previous notation. This thing should be something like this. Okay. So what we are trying to construct is what is the corresponding H prime in terms of this new set of cross-grain variables. Okay. I think that would be logically more clear. Let me try to emphasize this line, there's no approximation. You just divide the description of your configuration into a different way of naming scheme. And this line, to some extent, we haven't done anything, but we will try to do that in our next lecture and see how to achieve that. Okay. So let's pause here and take a 20 questions. Just ask me. Then in the next lecture, we'll continue and see how we proceed from here. Okay. Bye.
原本只有一个 triangular lattice 的 case，
这个
它不是就是会有 up down， 然后你会增加一个你不知道填什么。
你说这个吗？没有，这个不是我们要讨论的，因为这个太复杂了。
所以你把它简化成，你如果看的是一个 cross grain， 你就不用管里面是什么了。
不是。我们现在讨论的是 ferromagnetic 就是大家喜欢排同一个方向。
这是讨论同一个方向。
那为什么我们要讨论 ferromagnetic 的原因，只是因为这是一个比较简单的 case。但是我为什么要提到 anti 一个很有趣的东西，然后有 frustration 出现？但是这个 frustration 是在这个系统里面很重要的物理，你用一般的 cross grain 你没办法处理它。这个可以处理，但是你要做一个很奇怪的 mapping。就是有点太遥远，不过我还是讲好了。反正你现在就是 up down， 然后这个不知道是多少嘛，就这个可能是 up 或 down， 抱歉，它可能是 up 或 down。那不管，因为呢，为什么不管呢？因为你总是会发现一件事情是，总有一个棒不高兴，就是你现在你这个是 up down， 所以这个棒是高兴的嘛。你如果是 up， 这个棒就不。那如果你是 down， 就变成，如果这里是 down， 就变成这个棒不高兴。所以说你就发现一件事，这种 frustrated 的 anti-ferromagnetic order， 它 always 会有一个棒都是不高兴。那有一个棒不高兴呢，你就可以做一件事，就是你有一大堆三角形。你有一个条件是，每一个三角形，就是任何一个三角形，它一定会有一棒不高兴。那你就遇到一个问题，怎么样聪明的描述这件事？这样，那一个聪明的描述它的方式是，你把它 map 到一个六角形的晶格上，然后呢，这个六角形你可以放一种东西叫 dimer。那这 dimer 的游戏规则就是，dimer 就是它游戏规则就是它是一个占据两个 site 的东西，然后它一定是最近的地方占据。然后比方说像这一种 ，OK， 这就是六角形，然后它有3个 dimer 这样。那你的游戏规则就是，如果你的 dimer 有 cross 这个三角形一次，这个三角形的边就是不高兴的那一个棒，就这个是不高兴的，这个是不高兴的，然后这个是不高兴的。OK， 你说那我为什么要做这个 mapping？ 原因是因为一旦你做这个 mapping 以后，你的模型从原本的 triangular lattice 变成一个 dimer model on honeycomb lattice， 然后如果照这个画的话，这个是 dimer， 这个是 dimer， 这个是 dimer， 那个。然后刚刚的条件就是每一个三角形里面要 exactly 有一个不高兴的棒，就会变成每一个 lattice side 一定要连接到一个 dimer， 所以它就变成一个 dimer every side is covered by one dimer。然后你可能问说，那我为什么要做这个奇怪的事情？那事实上就是这个东西，如果你把它做另外一个奇怪的画图，就是你把就是这里有个 dimer 吧，你画一个平行四边形，然后它的中心是和那个六角晶格是接在一起的，然后你把它框起来。
你就可以选一个新的那个，
你就会把它 map 成另外一个很奇怪的东西，它看起来就是一大堆
四角形
立方体，然后排在三维空间里面的样子。这是一个非常不正常的东西，但是它存在这样。
它是2维的，然后你把它变成像3维的东西。
就是你看起来有点像是你有一个3维的 豆腐一样的东西，有没有？然后你一的方向看下去，这两个是 one to one 的，可是这是一个非常不明显的你正常人不会看到的东西，但是它是 one to one，OK？、那你说，那我为什么要 one to one 把它变成这个东西？你如果这个是沿着
1 to 1的意思是它的 spin，
就是这里的 spin configuration map 过来是两个会对一个，原因是因为 IC model， 因为你喜欢或不喜欢，就是你可以这样或这样子嘛。
它变成1对1。
对，但是一旦你变成 dimer 以后 ，dimer 和这个立方体的 mapping 是1对1的。然后这个立方体的 mapping 呢，如果我们现在是在沿着111的方向看，如果你111垂直的平面看它，它看起来就像是一个这样凸起来的东西，你知道？就是我把它画出来，它有点像这样子。然后后面这里有一个，你知道吗？有点尖起来。那你说我为什么要做这件事？因为如果你从侧面去看这个东西的 H， 就是你用这个高度去当做你的 field configuration， 就是这里叫 H， 然后每一个点你都可以定一个高度 H 嘛。你会发现你的在二维情况下，如果今天你是就是你的 dimer 是 fluctuating 的，那意思就是这个立体的平面也是一直在 fluctuating。然后这个立体的平面的 fluctuation， 在最简单的情况，它会是这种高线 fixed point， 但是是二维的，然后你就可以做了。然后这个东西和 XY model 有关，反正很有趣，但是我没办法现在直接讲，就是它可以，你经由一连串的 mapping， 你可以把它做到可以解的东西。但是如果以解我们现在的 ferromagnetic 的 Ising model， 不太适合走那边去，因为你会得到太多的 information。但我们现在只想要讲比较单纯的 information， 就是针对 ferromagnetic Ising model， 我们可以得到 RG 的什么行为。那 anti-ferromagnetic 是另外一个 beast， 就是它很好玩，但是它很难。对。
还有另外一个问题，其实跟 homework， 我一直把这个东西嘛，因为第二个问题是这个东西嘛，我一直把它往下写，它的注是叫你找一个，好像最后会有一个这个形式的，这个是 G， 然后 K， 然后加上一个，好像是这样，但是我怎么写，我都觉得它跟这个是一样的。所以我最后还是写到这样，就是我把它，还是我要把那个作业交出来了。
没有，你是说你插了前面那一个是不是？
对啊，因为我直接套你前面的条件就得到这个答案啊。
哦，那是因为前面有丢一些东西啊。你如果把那些东西恢复的话，就是你前面应该是第二题，我跟你讲说，你不要搞什么奇怪的 scaling factor， 但如果你把那些 scaling factor 放回来，你应该就会有它了。等一下哦。
哦，所以你那个等号是没有 scaling factor 的意思？
就是你有看它的这里的说明嘛，对不对？你看 compare 2和3 if we ignore the prefactors， 这个东西可以连过去。
你是说，
如果你不要 ignore 那些 prefactor， 你应该是可以弄回。
所以这个等。
这个只是有点像目标，或许我以后不应该写等号，应该要说它应该是一个目标，希望它会长那样。但是，对，就是你先不要管，所以就是第二题 B 的时候，你先不要管这个，你就认真的做，然后
认真的把这个东西
就是你不要太相信后面的那个 statement， 这个可能有点 confusing。就是你先用这个做就是了。
后面那一段没有看的。
对，就是然后就是你如果
为什么写 N 次都是这个答案？
如果你直接拿那个，你可能会真的没有那个 prefactor， 但如果你认真的做，你应该可以做出这个东西来，对吧？试试看。对，
应该就是把它 transfer 把那个这个3次方，这个3次方就是2的平方，然后把它变成 natural log， 上面就有一个 information
之类的，就是你应该就是小心这种前面的 factor， 然后把它塞进去。对， 试试看。不过反正你们不用太担心啊，就是得到什么就写什么，对吧？有话说。
所以等于是我把这么丑的什么跟水太个天分三四方面，通通都带到它哪里让它重算的。因为不是跑对吧？这个东西嘛，它是这里下来，有一个连层拍嘛，对。然后它最后出来，它是会有个鱼在前面，所以就是它这里做这里同的还有下面的鱼的方式。而且它其实除了这个上面，这个有点难说，是这样子。我是打算直接把它搬到一个那个上面，就是这里就变成一些肉，然后我把它放到这样是的，我比较轻一点，我是直接就假设我已经知道答案，就这些哦，我就有一个 exponential 去 k 然后再还有这个你说它是谁的？就我先说，你说这个谁的？我是就去给 from 啊，对，差不多类似的。对，然后再这样打，你错，这样子错过，对，就是原本。但这个你是直接把它的东西也可以。好，那如果我是直接说，它是可是你不把这一项放在你的东西里面，我知道后面那一项可以。后面这一项，过后的这个一样的意思啊，你取肉。其实这个上，不把它放到，这里可能因为这个上就，就课上，对，因为你可以用机器看这样，就是然后它去这里，别往对，在经历使用的时候，这个哦，我知道了，这跟前面的方法
我看大家好像都比较喜欢期末考周给报告，就12号和5号这一段时间。
12月底好赶，
因为12月底比较赶，对吧？你们现在开始繁忙。期末考周是12号，你们有其他期末考在12号那个礼拜吗？还是还好？电动，好了解。所以如果有电动的话，就可以早一个礼拜报一报，可能就可以错开之类的。了解。你们要去物理年会吗？你也要
去看看。
了解。物理年会还蛮赶的，刚好就是期末考周结束以后。哦，了解。
handwriting 是要在口头报告完之后多久交出
来？基本上都是 deadline 都是12号了，就1月12号。如果你是12号报，你就12号交。啊，如果你是5号报，你就还有一点时间可以改这样。对，我现在还没有确定就是大家报告的顺序，但是我应该这个礼拜就会确定，然后寄给大家这样。理论上就是看大家的 preference， 如果比较喜欢5号，就是5号报的，我就尽量让我们5号报这样。啊，然后如果排不下，那就照学号排这样。大概是这样。所以会再跟大家讲报告的顺序。就是像我刚刚讲的，就是试着把逻辑什么的讲清楚，然后你们有 page size， 大家没记错，就试着把东西精简的讲清楚，你不需要就是以篇幅取胜，没有说什么写。推导的话，我建议是找到关键的方程式写就好。那个方程式，如果你真的很想推导的话，你可以推导，然后放在 appendix。就 appendix 你可以加很长，但是本文的部分我会建议你，就是为了让逻辑比较精简。我通常的写，就想象你在写 paper， 就是你有一个关键方程式，然后那个方程式代表什么意义？
太详细的不太知道怎么推了，就知道它物理在干嘛。
你也可以这样，如果你想推，你可以推，但如果你觉得推起来太困难，但是你觉得你比较想要知道它物理的概念是什么，那你就试着去了解那物理概念是什么，然后讲你的 reasoning 和你的解释，这样就好了。那重点不是针对那个方程式是什么，重点是这个方程式是重要，是因为它跟前面的有什么关系，还有它会怎么引发你后面的一些结论，这种逻辑性的东西要把它抓出来。因为我不希望你们就是花很多时间在推导这个不知道怎么导出来的，然后推了很久，然后不知道整个你们在报告的主题大概是长怎么样，因为这个反而我觉得不是那么重要，就是以做研究来说，我觉得比较重要是你们知道逻辑是什么，然后大概方向是什么。那这个课程毕竟不是你写论文嘛，如果你要做你自己的论文，你的推导就真的要写清楚。但是毕竟他不是做这种事情，反而比较像是让你们去有一点机会去尝试不一样领域，然后试着用一个比较大的角度去看，如果你要进去一个领域，你怎么去 identify 重要问题是什么，然后怎么去跟大家诠释你看到的重要问题为什么有趣，比较像是这样的练习这样。那当然也要跟统计医学有关啦，你做到完全跟统计学无关的时候，就不太适合这样。所以我会跟你们讲哪些是可能比较 OK 的。如果你们寄信来说没，应该基本上就没问题啊。对。然后报告内容基本上没有太大的限制，主要就是篇幅还有逻辑要抓好，然后字不要写太小，大概就这样吧。就是随便，就是你觉得看起来舒服，你觉得喜欢怎么样，就我很 free 的，你也可以用 paper 的 style， 或者是你喜欢的 style。OK。 好，所以我想我们就Okay, so I think we will continue our discussion. So the first thing I want to emphasize is that right now we are discussing about the ferromagnetic case because like it is the only case that we can discuss. It's more like it is the simplest case to demonstrate how RG works. But in principle, you can, of course, discuss in something that is more complicated. But so, for example, like the frustrated effect, but we basically try to reserve that for more advanced courses. So if you are interested in, you can try to, explore something related to that. Okay, so back to our line. So basically, we are trying to study the ferromagnetic Ising model on the triangular lattice. So we try to define what are the cross-graining process for this model and try to get it a block spin type of degrees of freedom using this majority rule, which assign the block spin by the sign of the total spin on a particular triangle. Okay, so according to this cross-grain scheme, we also know that the scaling factor for each of these steps is square root of 3. Okay, so this is a well-defined process. And the logic is from the exact solution, we know there are some key parameter. One is yt and the other is yh. And we got this result just because we want to compare it with the result that we are going to get using the and see whether this procedure is okay or whether it creates something useful for us. Okay, so now we want to represent the cross-grain Hamiltonian using this new degrees of freedom, this block. So right now we try to use a notation that each microscopic configuration of the original spin system can be two sets of variables. One is the block spin SI, S capital I, and the other is the more microscopic configurations within each triangle, which is represented by the sigma I. Okay. So basically, sigma I will have 8 configurations that they are all listed right here, and 4 of them will correspond to the block spin that have +1, and 4 the block spin that have -1 spin number. Okay, so the green line, let's emphasize here, is trying to emphasize the partition function. Original configuration, to write it down, is exactly equivalent to the partition function that we use these new sets of variables to describe them. Okay, so the goal that we are trying to achieve is that we want to consider the new Hamiltonian after the transformation, or like after the cross-graining, which is called H prime. And now this H prime is determined by the block spin configuration SI. Okay, so the question is how to process this step. Okay, so now we are going to move on, and so let's try to get back to our Hamiltonian, but try to first understand what we are doing right now via the perturbation theory argument. Okay. So, in principle, if we try to label the bonds using this dashed line and the solid line, where the solid line represents the coupling within the block spins, and the dashed line describes the coupling between the block spins. Okay, so the total Hamiltonian, or the original Hamiltonian of our ferromagnetic Ising model, can be written as H naught plus V. And what is H naught? H naught is basically described by this solid line. It represents interaction within the block spins. And represented by this dashed line, represent the interaction between okay. So if I use the color pink to represent the H0, then the H0 interaction, and if I use the color green to represent V, these are the V's, okay? So divide our system in this way because now you will see it is useful for our later calculation, but let me try to write down the expression first. So in this more suggestive way, then you can see oops. You can express S0, H0 and V using these Hamiltonians, okay? So basically, I labels the pink triangle. The coupling are basically within the pink triangles. And IJ are not the same because now the coupling of this dashed line must belong to different pink spins. I and J now, the little I and little j now belongs to different block spins, capital I and capital J. And H0 and V, if you add them up, you basically recover the original Hamiltonian that we have, okay? So the purpose, or like the reason why we our Hamiltonian in this way is because you can realize that now these H0 are formed by okay, and this information will be useful for our later calculation. So let's try to move on and see what we can get, okay? So is that we are going to define what do we mean by average over the Hamiltonian H0. Okay, so this angle bracket with the subscript 0 or basically is the notation for average over H0. So suppose we have a operator that depends on the block spin as SI, okay? Then the average over the H0 means that you are basically summing all the possible little configurations within each block spins. And each block spin, you will collect them according to the block spin that's provided or specified at the very beginning. But what you need to do is basically you just consider all this spin configuration sigma. Okay, so when you are doing that, this operator A will also depends on the microscopic configuration, this little sigma I, and the corresponding block. Okay, and of course, because it is an average, so we need to divide it by the corresponding partition function as we did in the okay. So this is to some extent the definition about what is the average over H0 means, because you just sum over the corresponding configurations within each triangular bracket. Okay. So that's once we have this definition defined, then we ask what exactly is this object. Okay. So remember now H we can divide it into the H0 part and the V part. So let me just write it. So this is the new Hamiltonian with the block spin. It is defined by the summation over the configurations within the block. Now we divide the Hamiltonian H into two parts. The part that contains the decoupled triangles, and the part V that contains the coupling between the okay, and they are all described by this little sigma I, and basically that's it. So we want to try to we are trying to sum this expression. Okay, so like average over H0, you can express this. You can rewrite this expression a little bit by, dividing this stuff by exponential H0 my sigma I, and when you divide something, you just multiply the same thing back. I think I'm running out of space. Let me try to move it somewhere here. So basically, we are doing nothing. We just divide something and multiply something. Okay. So this line is exact, but you might wonder why I'm doing that. This expression is basically useful to interpret this first product as some kind of expectation value over V. Okay. So write it more explicitly. This thing is basically the expectation value of exponential V of Si sigma I not, and we have this thing. I'll just write it down explicitly. Okay. So this term is something that's obvious, but let's try to deal with the more obvious one, which is the H0 part. Okay, and this part is simple because at the diagram you see these pink triangles. They are basically decoupled. Okay, so learning from the previous statistical mechanics, we love decoupled stuff because the partition function just factorized. Okay, so this part, wait a second. Is a partition function of each triangle and raised to the power of m. Okay, so this m is just like the number of plaquette. Okay, so for one triangular plaquette, the partition function is basically defined like this. Okay, and you can just enumerates all the possible ways. A spin configurations. And a very useful way to enumerate them is here, because I have already done that. You just have A of them. And the conclusion that you're going to get is for the case where the block spin correspond to +1, it will equal to 3 exponential minus k plus exponential 3k. Okay? And this comes from the 3 spin up, and this comes from the 2 up 1 permutation. Okay? And there are 3 configurations of that. And for Si, the block spin equal to -1, you basically flip all the spin configuration, but because of the Ising coupling is Z2, so basically you got to say, okay. So this calculation for Z0 is not difficult. We'll just put it as if we know that. So now we are going to focus on the target that moment, but let's just try to write it out. The question is, what is this object? So function, usually it is very tempting to write down the expansion of the exponent for the exponential function. And because average is some kind of linear operator, so you got something like this, etc. Okay. So now we are going to make a assumption, or like the approximation, that we are trying to treat this dashed bond perturbatively. Okay, so we are kind of trying to consider this V as coupling is very. So you might say, okay, so the original Hamiltonian, of course, every bond is equivalent. So clear that I can consider it as a weak bond. Okay, but let's assume that it is weak and try to move on and see what is the influence. Okay, so consider KV is smaller than K, so we can do the calculation perturbatively. Okay, so let's try to make this assumption and move on. So, so one thing that I should write it out is to remind everybody that log 1 plus x, when x is small, it looks like this. This is just some tidal expansion. So what we are trying to calculate is this object. And the reason we want to calculate this is because we are looking for h prime. Okay? So in order to get h prime, what we are trying to do is take a log of this h prime. Okay? So what we really care about is the log of this object. So if we write down the log of this object, actually you're taking log of, as we mentioned, this exponential v basically is this stuff. So it's 1 plus v plus v squared by 2 and stuff. Okay? And as I mentioned, if we consider this thing to be small, then log of 1 plus x is basically x minus x squared. So we consider this whole object as x, and you just plug that into this expansion. Then what you are going to get is this log exponential v average over Hamiltonian h naught will be this. Okay, and if you have a keen eyes, you find this is what people call the cumulative expansion. So so if you re-exponentiate this thing, basically you got oops, sorry. Okay, so basically, this stuff is going to be related to h prime of Si. Okay, so let us try to be a little bit more precise. So h prime of this Si is effective Hamiltonian for the block spins. We'll now have two terms. One is m log z naught. Okay. So this is, coming from the decoupled. Okay. And you will need to add these terms. So in order to calculate this thing, the only non-trivial task for us now calculate this expectation value of V over average over H naught, or this V squared average over H naught also. So let's try to do it first order in V, and then we will do it for second order in V, and we'll see what's going on. Okay. So at this point, are there any questions? Okay. If there's no question, let's try to remind ourselves what is V. Okay. So V is basically summation over the spins I and j that are not equal with each other, and we have a bunch of these V ij. Okay. And let's try to take a example. Suppose we have I sitting here, and we have 1, 2, 3 spin, and they are coupled with another spin j, which has also 1, 2, 3 spin. Okay. So for this particular, the Vij can be explicitly written as the third spin of j, which is sitting right here, the first spin of I plus the second spin of I. So let me try to represent these spins. Okay. So let's try to use this simple one bucket to see what's the effect of the average over H naught. So we're trying to calculate this thing, and we know calculate Sj3 Si1 average over 0 plus Sj3 Si2 average over Hamiltonian 0. Then 1 and 2 basically, they are just equivalent. There's no particular reason why 1 is special and different with 2. So this result should be the same as twice the contribution of this of the coordination function. So that's one of the simplification we found. So the next question we are trying to ask is what exactly is this thing? Okay. So recall that this average over 0 means that the base that we are starting with is a decoupled. Because the triangles are decoupled, so because S3J and S1I, they belong to different triangles. So this thing actually can be factorized. Okay, because the base H0 is decoupled triangles, so this thing factorized nicely. So now it is a very good opportunity for us to understand what is this thing. So by definition, it is related to the partition function of these decoupled spins. And we want to sum over all the spin configurations, sigma j, within a particular Sj, because Sj now is like a provided, so we just sum them over. Now everything okay, so this is for a particular triangle, the corresponding Boltzmann factor, and we know what is the partition function for each triangle. The expectation value of Hj3, so we just put it right there, and we are summing over all the possible little spin configurations. Okay, and as I mentioned, these little spin configurations are basically by two cross-square sector. One is Sj equal to 1, and the other is Sj equal to -1. So for Sj equal to 1, you have, let's see, all spin up, or 2 up, 1 down, and the rest of the other 2, and -1, you basically have all spin down, 2 down, 1 up, and the rest of the other 2 configuration. So what you do is that you just plug that into this exponential. Then you'll realize that this Sj3 expectation value will be equal to if you consider the sector of the cross-grand spin to be 1. And it will be equal to the other answer, which is different with the previous one by a sign. If you live in the opposite sector. Okay? So what it means is that you can try to re-express this average value as this way. you use the cross-square spin, the block spin Sj, but now it times a factor. That is what we derived right here. Okay. So you can do the similar calculation for Sj1, but by intuition, you expect you got exactly the same thing, but all you need to do is you replace this Sj by Sj. And remember, this Sj is the block spin. So what you are getting is actually quite interesting, that this Bij for one of them, average over the Hamiltonian H0, you actually will get 2k, where this 2k came from the this coefficient. And now we know what is the expectation value for each of them. They basically provide the same functional factor, but now times the block spin correspondingly. So you got something square, basically this thing. And the block spin Si and block spin Sj. Okay? So what does it tell us is that if you look at the effective Hamiltonian of the block spins to first order in V, what you are getting is your coupling K prime is actually 2K times this stuff. Okay. So so this is the moment to have a slow motion. So this is the final result we want to get, because we basically connect the coupling constant K prime at different scale after we perform the renormalization group cross process. So now the question is a little bit different with 1D IC model. This equation actually have non-trivial fixed points. So we try to solve that to find fixed points. By staring at it, you know, if it is a fixed point, it needs to satisfy this condition. Right? So one trivial solution is that you just set K star equal to 0. That's good. Equal to 0. A second trivial solution is K star equal to infinite, because infinite is equal to infinite. So the non-trivial one is when you set to be square root of 2, 1 over square root of 2, then you take square, you basically kill this 2, and K star equal to K star, then you are happy. So if this object is equal to 2, equal to, let me write several lines. You can solve this, and it turns out you will find K star equal to 1/4 of log 1 plus 2 square root of 2, which is something like 0.34. But really matter. The point is that, in addition to 0 and infinite, in this 2D Ising model, we actually get a non-trivial fixed point K star. Okay? And this K star is non-zero, suggesting that there's a finite temperature phase transition in two-dimensional Ising model. Okay? And this is the paramagnetic phase. Wait a second. K star goes to 0, it means temperature is really high. It is the case where paramagnetic happen, and K star goes to infinite. It's basically the case where we have symmetry breaking and we have a ferromagnetic order. And this is basically the third one, K star equal to, is basically the critical exponent. Okay. So this is basically a very crude approximation, because in order to get this result, we make only leading order expansion in B. But indeed, there's a non-trivial solution that is developing. And if we compare with the exact solution, what Onzager found is Kc is actually 2.7, which is not too bad compared with what Onzager found. Okay? But it is just the start of this equation, because once you got this equation, what you can get also, know what is the, how the RG flow nearby this particular fixed point. What do I mean by that? Is because if we try to calculate the eigenvalue, reduce temperature, basically what you are doing is you try to take a derivative of K prime with respect to K, but evaluate it nearby the K star that you just got. Okay? And you can calculate that, it be 1.62, and this should be easy. You just plug that thing into Mathematica and just ask it to do derivative and put Kc or K star equal to 0.34, then we'll get. So why this value is useful? Because it is related to the scaling factor L to the power of yt. And we know scaling factor of L for one RG step is basically then you can get yt basically equal to something. But you can see this yt is probably. The reason is, this thing is 1.7 something. And if it is 1, it will be too large. So the expected value of yt. Okay. And the exact result of yt is that it needs to be 1, as we previously derived from Onzager's exact solution. So get the numerical value out, and then you can convince yourself it is actually not too bad compared with Onzager's solution. Okay? So that's good. The first order. So the question we can ask is, how about the second order in V? We can try to move more bravely, because in second order, what we need to calculate is this term. Okay? So if you write it out, it looks a little bit, scary, but each V you will have 2 spins. So to the second order, you will have 4 spins. And this is the first term that you are trying to deal with, and you should have K squared. The term you are trying to deal with is something like this. Wait a second. Yes. Let me try to. but they are all evaluated with respect to this decoupled triangle Hamiltonian. Okay, so the first thing is that by the structure of V, you already know that I and J must be on different blocks. Because by definition, V couples different blocks. Okay, so IJ must be on different blocks, and similarly, M and N. Sorry, this one should be N. Also must be on different blocks. That's also from the structure of IJ and N from V. Okay. So the thing that we use is that, okay, so in principle, we have blocks that looks like this. Okay. And if I sits here and J sits here, another block, let's call it I prime, and M sits on I prime, and I don't know, N sits on J prime. Okay. At the second order, we consider the case where I not equal to I prime, and J is not equal to J prime, which means that these two pairs of triangle pockets are basically separated. Okay. And if it is so, then we are able to use the fact that H9 decouple the triangles. So basically, we can factorize everything. Then this thing can be, everything is just factorized. Okay? But if that happened, it means that everything kills themselves by definition. Because you can notice the first term and the second term basically looks exactly the same. So if everything factorized, then everything kills itself. So if this happened, no contribution. Since factorize. Okay. So how to have non-zero contribution? In order to have non-zero contribution, you need to consider something that's more complicated. And the numerical factor, I'll leave it as an exercise for you to figure out, but I'll just tell you how these things kicks in. So consider the first order, we choose these two particular triangular pocket, and that will be, by definition, this is the I pocket and J pocket. But the I prime and J prime pocket, you can choose it in a way such that this is the I prime pocket, and it is coupled with the J pocket. Okay, that's one way of choosing it. And of course, you need to, went through some calculation to really figure out, what are the coupling constants, as we did in the first order case, where we can enumerate all these little spin configuration and just sum them up and find the result. And what you expect to have is that this thing should have something like Si, and here I belong to I, and some stuff like Sj and Sm. Sn over 0, okay? And here n belongs to J prime, okay? So linear order in B, we already calculate this object, right? And we also know this thing is proportional with Si. And this one, we also know it is proportional with Sj. In the middle, you will have some other contribution, but the point is that if you go to second order in B, you will have longer range coupling of your block spin. At linear order, you still a nearest neighbor because this blue I and blue J, they are nearest neighbor on the block spin triangles. But at second order, you develop like longer range coupling. Now, the block spin I can couple to block spin J prime. So basically, that's one of the scenario. But you can also choose another scenario. For example, you can have a triangle here, but the other triangle sitting, J double prime. So you will also have Si coupled to Sj double prime, and the red part will just give you something like Si coupled to Sj prime. Block spin lattice, these two are basically further neighbor interaction. Okay. So basically that's the effect, and if you what you will find is that you will have a modified coupling of your nearest neighbor coupling, some value that is like 1.77, and you will have new couplings like a second neighbor and third neighbor couplings, and the corresponding eigenvalues will be something that is smaller than these are what we call the irrelevant couplings. Okay, so in principle you can generate them, but they are not important. So as you perform this step more and more times, these effect will be suppressed. Okay, so that's what happened for the related to the coupling. So now I think I probably will not have enough time to finish the field. So maybe I'll just pause here and then see about the RG process. We can try to run the mechanism again. So let's try to step further away from the calculation and see what we are doing. So first, this is a type of cross-graining process. And this cross-graining process is just a relabeling of every spin configuration by the cross-grain spins Si and the more microscopic configurations described by this. And then we are saying that, okay, the partition function is still invariant because we are just naming our configuration in a different scheme. Then we want to ask if we sum over each tuples, sigma I, Hamiltonian that describe this block spins interaction. Okay. Then we said, okay, in order to do that, what we did is that we divide our Hamiltonian into two parts. One is described by this pink triangles. Basically, they are decoupled triangle parts. And those are described by these green bonds. And these green bonds basically couple these pink triangles. Then what we are doing is that we are saying that, okay, suppose we treat the coupling relation. It is not really obvious why you can do that, but let's try to assume that. And then once you do this kind of separation of your Hamiltonian, and you are able to get approximation for your effective Hamiltonian by doing something that's called cumulative expansion. Basically, you just expand this exponential b. And after some mathematical manipulation, you realize that the only to calculate is the expectation value of this exponential b operator averaged over these decoupled triangles, because the other part is basically a bunch of decoupled triangles you can deal with easily. So you do that cumulative expansion, and you realize that at least at the leading order, it is relatively simple to calculate. All you need to do is calculate the expectation value of this V. And why it is easy? Because all the triangles are decoupled. Expectation value factorized. Once it factorized, you can just calculate the expectation value for this single spin SJ3 using all the configurations constructed from this sigma I. Then what you realize is that the expectation value of this SJ3 actually is related to the block spin operator. Okay, it is basically proportional with the block spin variable. But the is that you got a vector. This vector is related to some of the structure of the partition function. This bunch of the exponential 3k and stuff. Then after collecting them, you realize that this is how after you perform this block spin transformation. And then that's very fruitful because you found, using this expression, you can find a non-trivial fixed point, which is the critical fixed point that separates two phases and to correspond to the phase transition temperature. And you compare that with the exact solution, and you found that, oh, it is actually quite nice, okay? Even though you don't know how to solve down, 2D IC model exactly, but it already gives you something really good. And then, recently, you can use that to calculate the critical exponent and evaluate this YT exponent. And it turns out that this YT exponent is just slightly below 1, which is the exact value, according to Onsager's solution. So you can do it better by considering it to V square, but you realize that, oh, you will generate more terms, but these terms will have a coupling constant that have eigenvalues smaller than 1, which means they are irrelevant couplings. So once you iterate this, newly generated term will be suppressed. And in principle, you can try to improve the value of the YT and stuff, but I didn't really specify that right now, but you will. Okay, so now I think we are a little bit out of time. So in the next lecture, we'll try to do the calculation, but for the field, and then we should be able to see how field transform the arch. Then we will try to move on to some other discussion about like what are the defects and what you need to be careful when you are doing this type of RG analysis in real space. Okay, then if not, please remember to turn in the homework and start preparing your final presentation, and have a nice weekend. Okay. So let's see how to turn it off. Let's see. Here it is. Hey, 可以，你可以给我就好。可以啊，你如果知道要寄给助教 email 的话，你也可以直接寄给你。对，还有第一次作业这个还没改是不是？天哪！你可以直接写信给他，反正他是我同学，我也跟他。哦，你可以直接，我可以直接跟他讲。你可以直接跟他讲，或者是你直接跟他讲好了，叫他帮你改，这样子就比较不会忘记。因为我觉得我应该非常容易忘记，我最近有。这是你的作业项。好，感谢。那各位同学还有人要交作业吗？还是大家都要直接寄给助教了？啊？交给助教，或者是放在我的门口信箱的信封袋里面。好。